Hello and welcome back to Advent of Code 2024, day 16. We're roughly two-thirds of the way through the Advent calendar. Things are starting to get tougher, I would say. Yesterday was a tricky problem to code. 14 was, what was 14? Fourteen was also required some good thought as well. Yeah, 14 was a hard one, I would say. 13? Uh, 13 wasn't that hard, but it was a bit it's actually easier than it seemed. Alright, 16. It's time again for the Reindeer Olympics. Let's turn the volume. Alright, Reindeer Olympics. This year, the big event is the Reindeer Maze, where the reindeer compete for the lowest score. Human historians arrive to search for the chief right as the event is about to start. It wouldn't hurt to watch a little, right? The reindeer start on the start tile, marked S, facing east, and need to reach the end tile, marked E. They can move forward one tile at a time, increasing their score by 1 point, but never into a wall. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1,000 points. To figure the best place to sit, you start by grabbing a map from a nearby kiosk, for example. There are many paths through this maze, but taking any of the best paths would incur a score of only 7036. This can be achieved by taking a total of 36 steps forward and turning 90 degrees a total of 7 times. Okay. Best means most? But why wouldn't you just spin around on the spot, wherever? Oh, lowest is best. Okay, that makes more sense. And easier to... I mean, most wouldn't make sense. You can just spin around indefinitely, so there's no upper bound. Lowest score. So this... And I alluded to this in yesterday's session. This is where we want to go to the next level of BFS. And go into Dijkstra territory, right? Because we've got distance. We can think of score as distance, where movement is distance 1, rotation is distance 1000. That's a pretty big difference. So you want to go as straight as possible, basically. I mean, the map is small enough that you could basically think of this as 1 and 0. It wouldn't be technically correct. Actually, wait, no. Okay, that's a big map. Yeah, no, we don't want to do that. I was thinking for the small map, you could get away with just saying, using breadth first search and saying movement is 0 cost and turning is like 1 cost or something. Would that even make sense? Anyway, for a big map, that's just wrong. So yeah, I think we just want to use Dijkstra. Okay. And I wonder what they'll do for part 2. Maybe have multiple reindeer on the map, because that seemed to be implied. It's like a race. Okay. So, good thing is we've got a lot of code we can reuse. Alright. So we'll take the pause class, definitely. And then, suppose we take the grid. Take out that. So, yeah. We've got... We don't need that. Row equals list.line.strip. We don't need to make it into a list, do we? We're not altering the map. Row equals line.strip. So we're looking for the reindeer, which is S. Excuse me, and E. Right, if S in row start equals that, sure. And then row equals row dot replace S with nothing, with dot. I mean, what? Yeah, this makes more sense. I don't want any other symbols on the map. And then got if E is in there, then we want to look for E and say end equals row dot. Don't we use find for strings? I don't know the difference. And then grid.append row. So that should get us the map. So we want, let's take a look at this. Sooner or later we're going to need a grid class. Should we do that? There are going to be more problems involving grids. It would be nice to clean this up a bit. I don't like... So grid, accessing elements of a grid. I keep typing this. I keep doing this. Grid, blah, blah, blah. Something dot I, blah, blah, blah. Something dot J. Alright, screw that. Let's tie this up with a proper grid. So do we want to make this a data class? So this means it's going to be the grid will be fixed. We don't like modifying the grid. We can change it for some problems where we can modify it. It's just risky to do so. Right, so let's say tuple of string. Is that even how you do that? I think you need a... that. So when we're making this, we don't actually want to put Okay, we want to... Okay, so we make a list of strings. And then afterwards we say... grid equals. So we want to actually tie it up as a grid with tuple of cost grid to a tuple. Is that fine? It doesn't like that, but that's because grid is... It doesn't know what grid is. Okay. So... that's that. Then we want... grid... want some methods here, don't we? Just say, can we... define... width or height, return length of self dot grid, define width, return length self dot grid 0. What else? So now we don't need... Can I turn this Cat8 E302 off? I don't actually care about leaving 2 blank lines instead of 1. Can we ignore errors like this? Duplicated code fragment, 10 lines long. What? How is that duplicated code fragment? Can we turn those errors off? Okay. Turn those errors off. Okay, let's just try and reduce the amount of things we get. What is the complaint about this? It's a duplicate of 15? But 15 is not... What? Shut up. Okay, get rid of this. We don't care about 15. Close 15. Alright, so... the important thing for grid is define rep this is where we're going to print it for O in self.grid return, hang on. Well, what does rep do again? Is it rep or str? I think it's str. str we care about, right? So we want, so for str you want to return line break dot join self dot grid. So let's try that. Print grid. Yes, that's much nicer. Should have done this a long time ago. Right, the other thing we also want to do is to access elements so that we don't have to keep indexing into a list. So we just say get we'll give him pause. So it's actually going to be return self.grid pause.I pause.j. This, I think we can do this, can't we? So alright, that's so much better, isn't it? Now, we don't want to modify this grid for this problem, well, at least for part 1, so that's kind of safe. Neighbors. Alright, so now where did we last use neighbors? 14 like this, okay. So now inbounds is a method which doesn't make sense for pos. Pos is just a vector. It doesn't know anything about the scope of the universe it sits in. It just returns neighbors whether or not they're inbounds. It doesn't know that there's even a grid that it's sitting in. Grid is the one that would care about stuff like inbounds. So neighbors, we'll have two neighbor methods. One, which is for pos, and this just says define get neighbors for delta and pos, blah blah blah. Yield self plus delta. That gets neighbors. While we're at it, let's also define string. Actually, we don't need to, because that's the point of data class. Data class already comes with a definition of string, and it's just going to be like I equals so-and-so, j equals so-and-so. But for grid, we want to add in the line breaks. Like, if we didn't... Alright, let's see what it does. So let's comment that out. So we're not overriding string now. Now we print grid. And now it does it as one line. I mean, in many cases, that's what you want. That's, for a list of strings, that's a sensible default. But we want the line breaks in there. So get neighbors. And now for grid, we want get neighbors for a given pos. So we say for neighbor in pos dot get neighbors. So all for the four vector neighbors, we want to check that this is actually inbounds in the grid, because only grid knows about the grid, right? So Now the thing is, there's walls here, so that's never actually we're never actually going to end up caring. But it'd be good to just complete this grid class anyway. So we want neighbors that are not walls. Should we actually say get walkable neighbors? If so, 0 is less than or equal to self dot width height is less than pos dot I, and we want that pos dot. Okay, that is wrong. So it's I is within the height and J is within the width. If self dot get pos equals dot yield, so it's not pos, it's neighbor. Okay, so we've got a way of getting neighbors. All right, that's a whole bunch of things. Now the actual Dijkstra algorithm we want to write, I would say we write over here, because it's not really a grid method. Well, it is a grid method, but it's not really a standard grid method. It's very custom. We have custom logic in there, weird scores and stuff, so I don't think we really want... Actually, no, there's no reason we can't just put it in grid. Yeah, we'll make it a grid method. Alright, so, Dijkstra. So we want a start and an end. Find shortest path to I just realized walkable neighbors is irrelevant here because we're not turning, right? So we don't actually want that. We have this notion of direction as well. Let's comment that out for now. To goal. Okay. So let's say start pos, because it's not the start state, it's the start pos. Start equals, it's going to be a tuple with the start pos and the direction. The direction is fixed at, well, we should supply the direction. Okay. Okay, so that's the starting state, because direction matters. Direction is part of the state. And then So we need all the things. We need a visited equals set. So we're going to need a priority queue, aren't we? From queue import priority queue. Okay, so queue equals priority queue. Queue dot put start. We need dist. Dist is going to be a dictionary which maps start to 0. That's telling us the distance. Do we actually want to store the path? No, we just want to find the lowest score. Alright, so if we wanted to store the path, we need a came from map, and then we have to have a separate loop at the end which reconstructs the path. Might come up in part 2. For now, we don't need to do that. So we've got start state, start 0, visited. Okay. While not q dot empty current equals q dot. Wait. Q dot. So we want start and the distance, right? The other way around. We want distance start. The only thing is we can't order pauses unless we just add a ordering, which is kind of a hack. Like, you wouldn't really want an ordering on pauses. Well, you could do. Well, okay, we could say, I don't know, lexicographic ordering is the ordering. Yeah, okay. It's not pointless. So we want to say return self.I self.j is less than self other.I other.j. That has a use if you just want to order them. So now we are allowed to do this. So current equals q.get. Well, yeah, unpack it. Current pause, current dart equals q.get. So what happens when we get this? Oh no, this is wrong. So we got d current equals q.get. That gets the distance. Now, there's a thing we want to check here. If we found a shorter path to current, then this is useless. We can just discard this. It's basically lazy deletion. So we want to say if dist current is strictly less than d, then this is not the shortest path. So we want to say continue. So that means we put this in the queue at some point, but then we found a shorter path to this node. So it's, we want to lazy delete this. So if I don't know if there's a queue data structure which supports an efficient deletion, but this is how I normally do it. So if, okay, so we know at this point we know we've taken the smallest element. Why would this happen though? If there was a shorter distance, oh, we would have already evaluated the shorter distance to current before. This is just floating around in the queue, so we want to get rid of it. Actually, you know what? I think the better thing is just check if it's in the visited set, right? Expanded. I think maybe we call it expanded. If current in expanded, continue. Alright, so we want to expanded.add current. This is when we expand a node. We're never going to deal with that node again. Alright, at this point we want to check neighbors. So there's three possible neighbors. Go forward, turn left, turn right. So going forward is just that. If self dot, so we want if forward neighbor is walkable. Or just say we don't care about inbounds because we're never going to hit a wall, so we can just cheat and say maybe we should actually. Yeah, we'll make an inbounds method because I think at some point we might actually want it in a future problem. So this is just that. It's inbounds. It's looking at other. Okay, so self dot is inbounds forward neighbor and grid dot get I have an idea. When we do get, if not is self dot, or say if self dot is in bounds pause, return that. Return none. Alright, so if grid.get forward neighbor, so this would it would just return none if it's not within bounds, equals dot then neighbors dot append forward neighbor, but that's we have to add the cost as well. So the cost is 1 for moving forward. Okay, so that's 1 neighbor done. All right, and then we want turning. Okay, so turning. I think we need a rotate method. We did this before, didn't we? When was that? Early on. Let's look through all of these. 6. Rotate right, there we go. Rot right. And rot left. So rot left is going to be just the other way around, isn't it? So that and that. So these neighbors are always valid. So they maybe have been visited before, but they're always valid neighbors. So neighbors dot and 1000. So we need the full state, don't we? So this is going to be current direction. So keep the current direction. Otherwise, we want to do. It's going to be current pause current dot rot left. There's 1000 to rotate left. Thousand to rotate right. Okay, so we've got all the neighbors. For cost neighbor in neighbors. Okay, so we say So first of all, if neighbor is... So the total dist is going to be dist of current plus cost. So that's the distance it takes to get to this neighbor. If neighbor not in dist, so we've never reached this neighbor before, or it was in there, but we found a shorter distance. Total dist is less than dist neighbor. Then this is the new best distance. So we want to say dist neighbor equals total dist. This is the new best distance to this neighbor, and then we want to pop it on the queue. Q dot put, so it's going to be total dist neighbor. All right, that's Dijkstra written from memory. Oh, or the goal check as well. Goal check. If current, so the position is end, we finally return the distance we took to get here, and that's the answer. So as long as we're always expanding the shortest distance node each time, then whenever we expand the goal, it's guaranteed to be the shortest possible distance that we could ever take to reach there. Oh God, okay, that's a big chunky method. Let's try it. So we want print grid.dijkstra. So the start pause is going to be start direction is going to be, I think we'll have to double check this, it's 0, 1, so looking to the right. And the goal is end. So they're starting to the right. Facing east, yeah. Alright, run it. 106512. So many things that could go wrong here. Correct. Alright. So now that you know what the best paths look like, you can figure out the best spot to sit. Okay, fine. Every non-wall tile, S, dot, or E, is equipped with places to sit along the edges of the tile. While determining which of these tiles will be the best spot to sit depends on a whole bunch of factors. The most important factor is whether the tile is on one of the best paths through the maze. If you sit somewhere else, you'd miss all the action. So you need to determine which tiles are part of any best path through the maze. Damn. Okay. How many tiles are at least part of at least one of the best paths through the maze? Okay. So we have to adjust this to... Okay. So I think this is backtracking from the goal. So so when we do this, we just want to break, right? We know what the best distance is. So here, we now need to do stuff. I'm gonna need more coffee for this. So I think now that we've found the goal, we want to find all paths that led to that goal. Now I'm going to have to turn off my microphone until my kettle is finished. Hello, DJ. Got a bit of a it's a bit of a textbook question actually, but it's a tricky textbook question. It's full implementation of the Dijkstra's algorithm, which lets you find the shortest path from A to B. So we've done that. We've found the shortest distance, which was that whole bunch of code there. Now, they want us to find the full set of nodes. Basically, we want to find all shortest paths to the goal. So normally you only find one arbitrary shortest path and return that. But we want to find all shortest paths. So I think we want to now take the goal and walk backwards towards the beginning. We want to simultaneously walk backwards through all the paths. And that will give us all possible paths, right? So, let me do this. Let's say, so if we got as far as here, we found what the shortest path was. Let's say Q. So we want to make a stack. Let's say. This is a whole different thing now, so I don't think we want a stack. We want a we don't want to revisit nodes because we otherwise, if like 20 different paths all join at a point, then we'll re-evaluate that point 20 times. So let's just say Q equals that, visited equals that. So end state equals we actually need to know which way we're facing when we reach the goal. So if current 0 equals end, then we say end state equals current and breakout. So we now know what the end state is. So we pop it on the queue. Visited equals set. I suppose we can put the end state in there as well. Okay, so While q current equals q.pop. Let's say current pos current dir. Let's q.pop. Well, no, let's just do current equals q.pop. Distance equals dist current. We might not need to expand that right now. Current pos equals current. So now we're at this state and we want to go backwards until we get back to the beginning. If it's the beginning, I suppose we can just drop out. Just say if current equals start skip this. We don't need to do anything with that one. Current pos, current dart is current. Alright, so now we want to go backwards, so basically take these three neighbors here. Backward. I'm going to call it backward neighbor. So it's current pos minus current dart. So then we add neighbors with that. So the new state is we're standing backwards with the same direction. And then turn 90 we do this. Rotate left, rotate right, doesn't matter which direction. Okay, so oh, we do need the costs. Alright. So we've populated the neighbors. For cost neighbor in neighbors, we're saying it costs this much to get from this neighbor to where we are currently. So if this neighbor is already in our distance queue with distance equal to our current distance minus the cost, that means that neighbor must be also in the best path, because we went down the best path to get to that neighbor. We then add the cost just to get to where we are, so that's a valid... It's hard to explain this now. It's a valid... It's not even a neighbor, it's a pre-neighbor, like a pre-node, a node that we came to get here. But there could have been two. We could have split up. We could have arrived at current via two different branches. So we're looking through all possible neighbors, checking if they have shortest distance equal to our cost minus cost. That means they are both shortest paths to get to where we are. Oh dear. So cost neighbor in neighbors if neighbor in dist and dist neighbor equals, so it's, we visited this neighbor, this neighbor isn't on dist table, that means there's a path to it, and the distance to the neighbor is the same as dist current minus cost. Hello, Hyperion. You doing Advent of Code? And then, that means this is about as complex as the Dijkstra in the first place. That means this is something we want to put on the queue. Q dot append neighbor and visited dot add neighbor. So the idea is, if we've done all this, the queue is empty. Visited should now have the full set of, what is paths? So the set of nodes, because we only care about the individual cells. Fortunately, I don't have much time this year for Advent of Code, yeah. It's a lot of work, and it's during Christmas, you know, when you're supposed to be with your families and stuff, but I'm here spending hours every day solving problems. Because that's more fun, isn't it? So now we want to. So what they wanted from us was best path pos equals set of state 0 for state in visited. So visited ties up the positions with directions. We just want to discard the directions. We just want to keep all the states. So that will just tell us the pauses. Then we want to return this to the end state. That's the answer to part 1. And the length of best path pause. That's the answer to part 2. God. This works. First time I'll be relieved, but there's probably a bit of work we need to put in. So we want print grid.dijkstra start. Okay, so we do the same thing. Alright, let's just run it then. And it crashes. State 0. Pause object is not subscriptable. Visited. Alright, this is wrong. Visited.add neighbor. Neighbor should be these should be tuples in visited. Visited end state. End state is a state. How did we end up adding a pos to visited? Neighbor is a state. So we're only ever adding tuples to visited. How did we end up with a pause? Also, another thing we should do is if neighbor not in visited, do that to avoid duplication, but still the problem is still going to persist, isn't it? Damn it. Alright, let's see what visited looks like. So yeah, it's a bunch of tuples. State in visited. There's also the advent of cyber I was interested in. What is that? I haven't heard of that. Is it a cybersecurity type of thing? What's happened here? Oh, that's right. I don't see any pauses. How did we get a pause? Exactly, maybe by try hack me. Oh, okay. I've never really learned any cybersecurity. I mean, I've done some mathematics behind like some core cybersecurity algorithms, you know, like RSA and prime factorization methods and stuff like that, but I've never really looked into the actual coding security side of things. Something's wrong with visited. Cost neighbor in neighbors. If neighbor in dist and this neighbor equals this color. Why would this happen? So it looks like we're correctly putting individual neighbor, putting neighbor states in there. What on earth is going on? All right, let's state 0 for state in visited. I don't understand this. For state in visited, print state. Let's figure this out. Why is there a none in there? State and visited. Oh my god, we've got pauses in there. How did they get in there? No, that's that. Get rid of that. Okay. It looks like we've got a none in there. Oh no, that's just the core being. Alright, so this is what is in. How long did you start learning Python? Oh, over a decade. Probably 2010 or 11. Probably 2010 is where I first picked it up. Used it for a coding project at university. Like we were advised to use C for the coding project. I was studying mathematics, and so most of my fellow classmates were using C, and they were struggling because C is horrible, especially for mathematicians who have never studied programming, and suddenly you've got to use this C language to try and write formulae and stuff. It's but then I've read about Python, and so I switched to Python, and I had a much easier time than my classmates. Oh, where did you come from? That's the goal. Alright, I think I know what might have happened here. End state. That is casting end state to a set. You're not allowed to do this. When you initialize a set, you have to do it like this in Python. Curly brackets and the thing that you want in the set. You don't write set. You don't do this. If I want a set with the thing with 0 in it, I don't do this. That's not valid. You have to do this. See, that's throwing a... I don't know what would happen if you did that. Probably wouldn't be valid, but there we go. That was the problem. Oh dear. Right, is it going to work now? One oh six five one two 563. What do we think? Is that going to be correct? 563 is a small number, but then it's number of tiles in the grid that is on the best path, so yeah, it's going to be small. Correct. Wow. We got both parts on the first try. That's crazy. That wasn't expected, because look at this. That's my Dijkstra method. I wrote all of this without testing anything. Ran it. It worked first time. That's not normal. In fact, I'm worried. To be fair, I've written Dijkstra from scratch so many times now. I always force myself to write it from scratch over and over again. I never just copy the Dijkstra algorithm from Wikipedia or from I don't know, from some site which has it. I always just force myself to write it over and over again from scratch, because it just helps hammer in the algorithm into your head. Like, if I were competing, then I probably would just copy it in from a library. But, like, just writing it again and again and again just helps you understand why you're doing each thing here. Like, if I just copied it in, that would have saved me like an entire hour, probably. However, standard Dijkstra would not have this backtracking bit normally. This is a customs thing, so you'd have to write this one yourself. Like standard Dijkstra would give you a shortest path to the goal. It doesn't tell you, it doesn't care which shortest path, it would give you a shortest path. But in cases where there are multiple shortest paths, you need to write this custom logic to basically do a backwards depth first search to find all possible paths that had the exact correct distance to match up with the goal here. I started programming at the age of 9. I'm 21 years old now. Okay. You started at a much younger age than I did. I started when I had just finished my mathematics degree, so it was like I was like 21 or something. And I didn't even like it that much. But that's because we were taught C, and it gave me a bad impression. And I almost was like, yeah, I'm never programming again in my life. This is not for me. Then I tried Python, and I was like, whoa, okay. Things can be fun. Programming can be fun. Yeah, C is not... I know a lot of people insist on starting with C or C++. They're saying that their logic is you need to learn all the nitty-gritty stuff like pointers and stuff to fully understand what's going on and all that stuff. I don't agree with that logic. I think having a student start with C or C++ is going to put them off and make them not want to carry on learning programming. Yes, it may be true that starting at that deep end will make you a better programmer overall, but there's a high risk of dropout. Or lack of motivation as a result. But that being said, some people actually enjoy diving in with C. That's fine. It really depends what you're doing. Like, it gives you more control over some stuff, but if, like me, you prefer usually doing scientific or data-oriented stuff, where you don't really care about the pointers and the garbage collection and all that stuff, you just want a program which does a sciencey thing and not necessarily as fast as possible, just reasonably fast, then yeah, Python is perfect for that. And that's why Python is heavily used in data science and becoming more and more popular. Like the libraries are gradually getting to the point that they are much faster than a lot of the classic data science libraries. Like a lot of people, MATLAB was common back in the day. I remember back in university, they started moving us from C to MATLAB, and they gave us like a CD, a literal CD, containing MATLAB, and we could use that to use MATLAB. But I stuck with Python when that happened. It was a good change though. Definitely students preferred MATLAB to C. Not a fan of MATLAB though. Like some courses in my computer science university used MATLAB. I used either the Python. I used either NumPy and SciPy, or I used Octave, which is like the open source clone of MATLAB. Just because I liked using open source stuff. I did enjoy C and assembly, MIPS architecture, because I was doing something I really liked, the modding of Nintendo 64 console. Yeah, exactly. That's one area where knowing that stuff really helps. Because in my community for Azure Dreams, which is like a PlayStation game, the coders there have been taking the game apart, and a lot of the code is basically, it helps a lot if you've done assembly type languages before, understanding how the memory is stored, how pathfinding for the enemies is written. It's all like rudimentary stuff. It all looks so hacky in places, like the way that the enemies work out where to go and stuff. It's very limited. Like they can only move, they can only move like 5 steps before the algorithm breaks down. And if I were writing it in modern pathfinding, I'd be writing it like basically what we've done here. This is pathfinding right here. But on the old architecture, you couldn't do something as complex as this with priority queues and all this stuff. So they had really hacky methods which were specially designed for the levels that you were putting them in. To be fair, PS1 games entirely were hacks that worked on prayers and dreams a lot of the time. Yeah. And I suppose that's also the reason we get so many bugs, but then again, we get so many bugs in modern games, so it's not like there were really any more buggy. The bugs have a different nature, I suppose, to bugs in modern games. Like, underflow is one of the big glitches in As Dreams, which I use to abuse New Game Plus, and what did I use it in? I might have used it in Bookless, probably not. It takes too long to set up, but... Oh, no, yeah, of course, I did use it in Bookless. So the Japanese version of As Dreams underflows the value of items, swords. So if you rust a sword over and over again, its value underflows. Like, that's the type of bug you wouldn't see nowadays, because nowadays people are using libraries for holding their integers and their variables and stuff, and those libraries, have existed forever, and a lot of them are open source libraries as well, so there's no risk of underflow like that. But that's cool. It gets you infinite money. So yeah, this was a good warm-up in Dijkstra, not only writing Dijkstra, but understanding Dijkstra. I could not have done that second part, the backtracking bit, if I didn't understand Dijkstra. So yeah, this bit here really tests your understanding of it, knowing how to do something a bit more custom, a bit more unusual. I'm trying to think if there's a simpler way of putting that in without having to write a whole separate queue. I suppose... I think there is. I think what I should have done, and this is something you normally do with Dijkstra, you normally have a came from map. So every time you go from A to B, you put came from B equals A in the dictionary. If I had done that, then backtracking would have been simpler. I would have just said, I don't need to have this bit here where I'm reconstructing the neighbors backwards. I just have to look through the came from... but the problem is... No. This wouldn't have worked. Because came from only gives you one thing you came from. Here, there's 3 possible things that could have came from, and they could all simultaneously exist. So at some point we did need to move backwards. Like walk backwards and turn 90 degrees. Yeah, I don't know if there's a much simpler way of doing it then. I mean, came from, instead of being a dictionary, it could be, well, it could be a dictionary that stores multiple nodes per thing. You store every possible node that you could have come from. But I don't think that would necessarily give you everything, though, because in Dijkstra you cut corners. If you find the shortest path, you don't bother expanding other nodes. So... I don't know. Alright then. Good problem. I think... I mean, Dijkstra's not something you can really come up with yourself. You can, but the way that you structure the data structures and the priority queue and all that stuff, it's... Dijkstra is something that was developed by, well, by Dijkstra, I guess. You can come up with your own, like, yeah. I mean, you can write it as a recursive method and just make sure you're not repeating nodes too often, but Dijkstra, the way we formulate it in Dijkstra is actually really efficient. This is something you kind of need to know your textbook pathfinding for. Day 16. Both stars in 43 seconds. Don't know. I mean, if you just copy your pre-written... Oh, 10 seconds is ridiculous. Like, there's no way you're solving the first part in 10 seconds, even if you're copying in. But, I mean, okay, if you're copying in your Dijkstra, pre-written Dijkstra library, which a lot of the top competitors do, then, yeah, you could do it in a couple of minutes. That's believable. Because you've already written Dijkstra before. The only thing you want to do here is make sure it matches the map we're given and add some custom logic. I don't know. Okay. Fewer people have solved it than usual, so it's taking people a while. Oh wait, this is my leaderboard. Captain Coda's leaderboard. Yeah, it's still, I would say, fewer people have solved both. So yeah, I think a lot of people are still working on it. I guess it's tougher. Smab UK is currently working on it, I imagine. Umara? Umara is keeping up. This... I wonder if the game engine would actually... I mean, the game engine definitely has pathfinding in it, so it would probably help a lot with part 1. Part 2, though, is where you need to override standard pathfinding and do something that's... I mean... In theory, it's exponential time, part 2, because there could be an exponential branching of parts. So game engines wouldn't normally allow you to do this, because it's inefficient. And I can't imagine any game situation where you want to know all shortest parts. Like, it's not something you would use for anything. So you'd have to write your own logic in there. Okay then, I imagine there's probably some people still doing this then. Let's have a look. Oh, this is Advent of Cyber then. The one that Hyperion mentioned. Alright, well, there's only one person doing it, and he's doing it in German, so leave it there. Alright, then see you tomorrow for day 17. It is getting tougher now. Problems can take 2 to 5 or 6 hours in the worst cases from this point on, so I'll have less and less free time. Christmas Day, though, they usually make it easier. The Christmas Day only has a part 1, and part 2 is just solve every other problem, which hopefully I'll have done. Though, if I fall behind with one problem, it could need some catching up. Oh. Yeah. Okay. See you guys next time. Bye-bye.